All right, so far the basic integration that we've done has maybe looked something like this. Okay, so maybe you've had something that looks like the integral of x squared dx. Okay, and based on the definition, whenever you integrate, you use power rules. So you get that power of 2 and you add 1 to it. So x to the 2 plus 1. And you divide by your new power. And then you put plus CO at the end, right? So this would become x cubed over 3 plus c. Okay, and if you ever wanted to check to see if you did this right, you get your answer. So x cubed over 3 plus c. And you take a derivative of it. So the derivative of x cubed is 3x squared. So 3x squared over 3. And the derivative of a constant is 0. Now if you reduce your 3's here, all we have is x squared. And you should notice that this x squared is found right here. Okay, so they should match. So whenever you take an integral, if you want to check your work, just take a derivative of it and it should give you where it was at first. Okay, so that's stuff that we kind of mentioned before with integration. Again, these are basic integrals. You know, we could do an integral of sine of x or cosine of x and stuff, but I'm just showing you the basic ones right now. But the thing is that they don't all look like this, right? All of the integrals that we do don't all look like this. So we have to sometimes use different tactics to figure some of these things out. So let me show you an example of one of these integrals that don't look normal. Now, I did mention to you guys before that we do not have a quotient rule or a product rule or a chain rule for integration. So if you see something that looks like it's a product or a quotient or a chain, then most likely there has to be a different way for us to do it. Okay? Well, this is the way that we're going to learn. Like there's more than just this way that I'm showing you now. But in BC, you'll learn about other tricks to integration. But in AB, you only learn the one trick, okay, which is integration by substitution. So this is what we do. We look at what we have, and one of the things you could do is you could expand this. You can get x squared plus 1 and square it, right? And then after that, multiply everything by 2x, and you have a really long polynomial expression, and then once you have that expression, you can integrate it normally. But there are other ways. So in this case, what we're going to do is we're going to use substitution. Now, I want us to notice a couple little things here. In order to do integration by substitution, you're going to get something in that problem that we have here that you want to take a derivative of that will match something else in that problem. So let me give you an example. If I take a derivative of 2x, notice that's a piece right here, right? That's right here, 2x. If I take a derivative of 2x, will it give me x squared plus 1? Whoops. Is this equal to x squared plus 1? The derivative of 2x? No. So this is not a good idea. Remember, the idea is to pick something whose derivative will give me another piece in this problem. So this is not a good choice. Now, let me pick something else. What if I pick x squared plus 1? So the derivative of x squared plus 1 is what? 2x. Does that match something in the problem? Yeah, right here. So this is a good thing, okay? So this is how we're going to approach this problem. Let me rewrite the problem here. The integral of x squared plus 1 squared times 2x dx. And this is what I'm going to do. I'm going to write my let statement. Okay? We're going to let u equal to x squared plus 1. Okay, let u equal to x squared plus 1. So let's take the derivative of u, du. Now I'm going to do this using differentials. That means I'm not going to write du dx. I'm just going to write du, and then the dx will be on the right side. I don't know if you guys remember doing that. That was section, I think, 3.8 or 3.9. So the derivative of x squared plus 1 is 2x dx. All right, so let u equal to x squared plus 1. So du is equal to 2x dx. All right, now check this out. X squared plus 1 is right here. Okay? 2x dx is right there. All right, so what I'm going to do is the following. I'm going to substitute those things in. Instead of the integral of x squared plus 1 squared, I'm going to write u squared. And instead of 2x dx, what do you think I put in? Du. Thank you. So du. So instead of integrating the integral of x squared plus 1 quantity squared times 2x dx, I'm really just going to integrate u squared. Well, what's the integral of u squared? What do I get? U to the third divided by 3 plus c. But what's u equal to? All right, so let's go back over here. X squared plus 1 cubed over 3 plus c. And that is the answer to our problem. Okay, so if I take a derivative of x squared plus 1 to the third over 3 plus c, my answer will be x squared plus 1 quantity squared times 2x. Okay, I would just have to use a chain rule. And I'll show it to you. Okay, but before we move on, any questions on this? We'll do some examples, like I said, for this, because this is new. Are there any questions on it? So notice the idea is to basically substitute for everything. You don't have to substitute for the powers. Sometimes the powers are necessary to substitute out. Sometimes they're not necessary. Notice I didn't substitute out this power of 2 right here. I didn't worry about it. I left it out. Okay? Because I know I can integrate normal powers. So that wasn't a problem for me trying to figure out, like, oh, how do I integrate a u cubed or a u squared or anything like that. But usually the terms that are in there, maybe the polynomials, monomials, binomials, those you try to get rid of. Okay, you try to substitute those out because that's what makes the problem hard. So let me just show you really quick, if I may, the derivative of, I'm going to do 1/3 x squared plus 1 to the third plus c. If I could just show that to you really quick. Now, since 1/3 is just a constant, I'm going to take it out. Okay, so it's 1/3 d dx of x squared plus 1 to the third plus c. Now, the derivative of x squared plus 1 to the third is a chain rule. So there's a 3 that comes down. I write x squared plus 1 squared. And then I got to multiply by the derivative of the inside, which would be 2x, right, plus 0, or 2x. And then the derivative of c is 0. Now, if I distribute the 1/3 back in, this is my answer. X squared plus 1 squared times 2x. which is exactly what we started with, right? We started off with x squared plus 1 squared times 2x. So again, you can check your answers for your integrals by taking derivatives and checking to see if they come back to the original value in the integral. Hopefully you guys haven't forgotten how to do the chain rules, right? My wife was joking around with me earlier saying like, she says, I should probably expect that my students don't remember how to multiply. She teaches 3rd grade, so she doesn't remember how to multiply. I'm like, I can probably assume the same thing. I'm like, hopefully they haven't forgotten their multiplication tables. Yeah, hopefully you guys haven't forgotten your basic derivatives, because they are important for you to kind of double check some of your work. Okay, so anyway, so this checks out just fine. Before I move on, again, any questions on the integration using substitution? All right, so let's look at a second example here. So example number 2, we're going to evaluate the integral of 5 cosine of 5x dx. By the way, a rule of thumb, though it doesn't always work, but it works a decent amount of times. A couple little things. One, usually letting u equal to the stuff with the power is a good idea. So x squared plus 1 and 2x in the other problem. I used x squared plus 1 because I knew that when I took a derivative of it, the power would come down, right? So I tend to let u equal to the thing with the higher powers. When it comes to trig, usually you let your substitution be the angle. Not always, but usually that'll work. So my angle here is 5x. Okay? So if I let u equal to 5x, right? So I'll just kind of highlight it here. Then what's du? 5 dx, right? So notice 5x, 5x, 5 dx, right? 5 dx, here it is, 5 dx. Okay, so let's go ahead and substitute this stuff in. So the 5 dx becomes a what? A du. So I'm going to put du right there. And the cosine of 5x becomes a cosine of u. Now, if you're wondering, well, why didn't we get rid of the cosine? Well, because we don't need to. We know how to integrate cosines and sines and tangents and all that other stuff, right? That's not an issue. I know what the integral of cosine of u is. I don't know what the integral of cosine of 5x is. Well, I do, but with substitution, I can figure that out, right? I can figure that out. So cosine of u is, anybody remember what the integral for cosine is? Sine, right? So sine of u plus c. All right, don't forget that plus c. Very common missed point, okay? So sine of u plus c. Now, u is 5x. So I'm going to write sine of 5x plus c. And that's my answer. And if you take the derivative of sine of 5x, well, you're going to have to do it using a chain rule because the angle is not just an x. So the derivative of sine of 5x, well, derivative of sine is cosine, so it'd be cosine 5x times 5. Or, as it says up top, 5 cosine 5x. So if you go ahead and take that derivative, you will get the same exact value. So dx of sine of 5x plus c is cosine of 5x times 5 plus 0, which is 5 cosine of 5x, which is, again, what you see right there. Okay, if you're wondering, well, what about the dx? Like, how come the dx doesn't show up? Remember, the dx is right here. So you would just basically put it in the back of it if you wanted to look exactly the same. But I usually don't tell people to do that. You're just looking for the basic integrand. Okay, that piece on the inside, you're looking for that to be the same. So let me give you a prompt to try on your own. Okay, then I'll give you some time here to try it out. So let's see. I want you guys to evaluate the integral of x times x squared plus 1 squared dx. So x times x squared plus 1 squared dx. So I'm going to give you a minute to try it out, and I'm going to pause this meanwhile we do that. All right, so again, if I were you, I would pick the polynomial with the highest power just to start. I mean, maybe I'm wrong, but you know, I always figure that should work. So I'm going to let u equal to x squared plus 1. Okay? Because between x squared plus 1 and x squared plus 1 has a higher power. So if you take a derivative of it, most likely it might show up to become an x to the first, which in our case it does. If we let the derivative show here, we get 2x dx. Okay? Now you might say, well, wait a minute. I don't have a 2x dx. I only have an x dx. Well, you could manipulate your result there. Notice I just want an x dx. So that 2 in the front, I'm going to make it a half du. And now it matches perfectly, right? X dx. So check it out. X dx is right here. X dx. And x squared plus 1 is right there. X squared plus 1. So let's see. Starting this off again, my integral of, well, I see my x dx there. Okay, what do I write for x dx? Half du, right? That's what's right there. Half du. Notice I do separate the du because I got to write some other stuff in there. And then instead of x squared plus 1 quantity squared, what should I write? U squared. Now that half is a constant, and we learned that there's a property that tells us that you could get the constant and move it out of the integral. So I'm going to move it outside. So what's the integral of u squared? U to the third over 3 and then plus c. Okay? Now distribute that half, so this becomes u to the third over 6 plus c. Remember, a constant times another constant is just a constant. So whether you multiply, add, subtract, or divide the c value, it just stays as c. All right, now u, according to our definition, is x squared plus 1. So let's write it down. That's x squared plus 1 cubed over 6 plus c. And that's my answer for this problem. And again, if you want to take a derivative of this thing, you can. Okay, there's nothing saying you can't, but go ahead and take a derivative of this, and you'll notice that your answer comes out eventually to x times x squared plus 1 quantity squared as your result. So the one small thing that kind of changed in this problem compared to the other problem was basically right here. Okay, the difference was that we had to clean up our du portion. Okay, it didn't match perfectly. Okay, the du, the derivative, was a 2x dx, right? And I didn't have a 2x dx in my problem. I had an x dx, but not a 2x dx. And that 2, by the way, does not refer to the power that's left over there. You can't say like, oh no, there is a 2, it's the power. No, it has to be an actual constant in front of a variable. So since it didn't match, right, at the very top, du equals 2x dx, since it didn't match, then I just got rid of the constants that didn't match it. And it's okay for you to do that. You can remove the constants, move them over to the other side so that your stuff matches properly. And once you have a match, then go ahead and do the work. You'll notice that that constant in the very next step, the half u squared du, you could actually just move it out of the way, right? It's just kind of like in the way. So you just move it out of the way. Eventually you put it back in and do your work. So that's how you would do a problem where the derivative doesn't match perfectly, but you can manipulate a little bit. Any questions on this one? So notice we take something that looks difficult, we substitute it so that it becomes an easier problem, right? In some cases, really easy problem, right? U cubed, right? Not a big deal. Or u squared in our case. So it becomes a lot easier. And then from there, we just kind of do the basic things that we've been doing, the general power rules, etc., and substitute back in at the very end. All right? So let's try a problem like this. And I'm not sure, let me see, how much time do we have? I forgot to write down the time. What time do we get out here? 34? Okay. So, all right, let's see. Example number 4. Now this one we'll do together because it's a little different. Same idea, but you're going to... Actually, no, this one won't be that much different. But it's going to carry over to example 5. So let's see. Evaluate the integral of the square root of 2x minus 1 dx. Now remember, a square root is a power, right? So I'm going to rewrite this as the integral of 2x minus 1 to the half dx. Now notice you might say, well, I don't have to do integration by substitution here because it doesn't look like a product. Well, it doesn't, but if you look carefully, it kind of looks like a chain, right? If this was derivatives, 2x minus 1 to the half power, you'd have to use a chain rule, right? You'd get that 1/2 and bring it down times 2x minus 1 to a negative half times the derivative of 2x minus 1 for a derivative, right? So this kind of looks like it would require some kind of chain to do. So what I'm going to do is what I've been doing with the other problems. I'm just going to look at the term with the highest power, which there only seems to be 1, 2x minus 1. And I'm going to let u equal to that. So let's let u equal to 2x minus 1. Well, the derivative of 2x minus 1 is just 2 dx. By the way, if you're wondering why do we write dx after every time we take a derivative, it's because we're taking a derivative of x's, right? So that's why we write dx. That's the reference that we're using, dx. Remember, this all relates to differentials that we did near the end of chapter 3. Okay, so since my 2x minus 1 matches this, and my dx matches this part, but that number 2 doesn't match anything there, right? Like, yeah, it's part of a power, but we don't try to use powers as references. So that means I'm just going to try to isolate it. So I'm going to bring it over to the other side. Half du is equal to dx. Okay, so half du is equal to dx. I'm trying to erase this. Here we go. So there it is. Dx is the same as half du. So let's go ahead and substitute everything back. So I get the integral of, now my dx portion is half du. You'll notice I always plug back in my dx portion, right? I don't go straight with the u value. I always put in the dx first. And then my u portion is the 2x minus 1, so it's going to be u to the half. Right? Because it's 2x minus 1 to the half power. So I'm going to move out my constant. So the half goes out. And I have integral of u to the half du. Now using just your basic power rule here, u to the half. When I integrate that, it becomes u to the 3 halves divided by 3 halves plus c. Because remember, half plus 1 is 1.5, or 3 over 2, right? Well, if I simplify that u to the 3 halves divided by 3 halves, it actually becomes a 2u to the 3 halves divided by 3 plus c. Because remember, you don't divide by fractions, you multiply by their reciprocals, right? So just that means u to the 3 halves times 2/3. Now let me go ahead and distribute that half. You'll notice there'll be some cancellation that occurs in the first one. So this ends up as u to the 3 halves over 3 plus c. Let me fix that 2 there. And now that I'm at that point, my u was a 2x minus 1. So this is a 2x minus 1 to the 3 halves divided by 3 plus c. So tomorrow, I'll save up 3 examples for tomorrow. So let me go ahead and stop it here, and we'll do the rest tomorrow.